Welcome back, everybody. So today I'm going to be talking about the effect length of a feature has on the tolerances that are applied to it. So in this situation that I'll be going over, I'm going to be referring to specifically parallelism. And just quickly going over the definition of parallelism, it is the condition of a surface or feature's center plane equidistant to all points from a datum plane or a feature's axis equidistant along its length from one or more datum planes or datum axis. So basically what that means, if you remember from my video on flatness, every point on that surface, we're talking about a surface, needs to lie between two parallel planes separated by the distance, which is the tolerance. For parallelism, it's very similar. The entire surface must lie between the two parallel planes separated by the distance, which is the tolerance, but then those two parallel planes that are creating the boundaries for the surface to lie within must be oriented relative to the datum feature that it's referencing. So if you're, this is sort of a tangent, but if you've ever looked at the orientation control chapter, you may have also noticed there's an angularity tolerant or angularity control. And if you've ever wondered what the difference between an angularity and a parallelism is, well, it's really parallelism as well as perpendicularity are just special cases of angularity. And the parallelism and perpendicularity sort of just take advantage of this implied 90 or 0 degree basic angle that we've got in the Y14.5 standard. Jumping into the scenario that we're going to be talking about. So let's say we've got two plates, and it's the same parts, two of the same part, and we're bolting them together. I don't know what these parts do. They have a width of 100 millimeters plus 5 minus 0, and then a length of 150 millimeters plus 10 minus 0. And this is something to consider when you're picking a parallelism for a bolted joint surface, is that the joint face angularity actually impacts the fatigue life of that joint quite a bit. So you can see there's a quick drop off after you leave 0 degrees, but especially if you go past, let's say, 1 degree, it seems like it drops off very, very quickly. So from 0 to 1 degree, it's quick, but then from 1 to 2 degrees, it goes to almost 0. So this is something that you should be considering when you're picking the parallelism tolerances for a bolted joint. So seeing that the sort of inflection point according to that graph is around 1 degree, let's say we want to keep the entire angular misalignment, let's call it, below 1 degree for the entire assembly. We can say that that's sort of the equivalent of saying half a degree per part. So how do we figure out what that actually means on our drawing for a parallelism? Because we don't talk about parallelism in degrees. We talk about it in terms of a distance between two parallel planes. So, well, we can do some simple trig. So if you remember from your high school math, if you look at a triangle, you have an angle, and then you have this height here, and then you've got the hypotenuse. And knowing two of these, you can find the third. So if we know the hypotenuse, which would be the length of the part, and we've got a target angle, we should be able to find this height here. So let's say we've got our 150 millimeter plate. Sorry, 100 millimeter plate is actually the number we'll be using. So we've got 100 millimeters. And we've got a target angle of 0.5 degrees. And this is our datum right here. We want to know what is the distance between two planes that are perfectly parallel to datum A what is the distance between these two planes that will give us this 0.5 degrees? And this happens to be our question mark here. So using some math, we can go sine theta is equal to question mark over hypotenuse. Do some rearranging. Our tolerance zone is equal to, and h is 100 times sine of 0.5 degrees. And we'll plug that into the calculator. 0.87, round up to 873 millimeters. So as the designer, we've done our math and done our research and picked this as the tolerance, and we've got justification for it based off of this joint face angularity. But then later down the line, someone says, well, why don't we just restrict or more heavily control the area around the nuts or around the bolted joint contact face, because the rest of this surface doesn't really do much. We don't need to control it so tightly. So let's just control the area around these nuts. So one of the easy ways someone might do that, or maybe they would just want to sink the nuts under the surface for some other reason, but they put a counterbore and then they say, well, this parallelism worked for this top face before. Why don't we just use the same parallelism for these counterbore faces? And that should give us the same results, keeping the joint face angularity below 1 degree for the entire system. And that's not actually the case, and I'll show you why. So what we've done here is actually quite sinister, because we've stolen the tolerance, but we haven't considered what that actually does on the part. So what we're hoping is that this theta is going to still be 0.5, and we've got this height here of 0.873. But we've changed the hypotenuse. Before, this was a length of 100 millimeters, but now this is actually only a length of 20. You might say, well, what if the designer is clever and they say 4 times parallelism? Well, keep in mind, parallelism is an individual control, which means that each one of these counterbores is able to move independently. So this actually does not help us. So let's do the math and see what this angle that we're actually going to get is. So remember, sine theta is equal to opposite over hypotenuse. So we can say theta is equal to inverse sine opposite over hypotenuse, which is equal to inverse sine 0.873 over 20 is equal to 2.5 degrees. And that's per plate. So the total potential angular misalignment in this system is 5 degrees. And if you remember that curve, the fatigue life absolutely collapses at like 2 degrees. So if we're at 5 degrees, this is going to be a very unreliable joint. So the conclusion of all this is that if you're going to make a change to an assembly or to a part that goes into an assembly, you have to re-review the tolerances. You can't just take a tolerance from one, revision of a part or one similar part and bring it over to another one, especially if there's, differences in the actual form. It can have quite drastic implications if you just blindly sort of bring tolerances over. Anyways, hopefully this helps someone catch a mistake that might happen. This is a fairly narrow example, but it applies to a lot of things. Anyways, have a good one.